Hello, this video is differentiation and integration of vector valued functions. So this has both formulas for R of t, the vector valued functions for both plane and space. So obviously the only difference is the space has that third component h of t that goes with k. And to find the derivative, we take the derivative of each component of your vector valued functions. Now, just like when you find the limit of a vector valued function, look what Stewie says here. The derivative of a vector valued function is a vector. So essentially, you're just taking the derivative of each component. So it'd be a vector f prime of t, comma g prime of t. If it's space, then you have comma space vector, comma h of prime of t. So it's real straightforward. I don't like, I don't let my derivatives get too gruesome here or whatever, so this should not be too bad of a process. So this is really pretty straightforward and easy. Take a look at this example right here where your vector valued function, r of t, is 4 square root of t squared times the square root of t, and natural log of t squared. So 4 times the square root of t would be 4t to the 1/2. This one's kind of weird written this way, but maybe it's good exercise for us to see something a little bit different. But anyway, for t squared square root of t, just multiply them together and add the exponents, and you'd have t to the 5/2. That would be ridiculous to do a product rule for that when you can combine them. Now, obviously, if that radical would have had like t plus 1 underneath it, everything I just said was moot. Then we would have to do a product rule. And then the last one, because we're not squaring the log, it's the natural log of t squared, I can bring that 2 down, which you don't have to bring the 2 down, but why not if you can. So we take the derivative. Now you see I quickly got out of IJK form and went to component form. So it's, obviously an instructor might want it in that particular IJK form, which is fine. Still do it the same way, but I tend to want to switch to component form whenever possible. Just I think don't have to write the I, J, and K is nice. So the derivative of 4t to the 1/2 would be 2t to the negative 1/2. T to the 5/2 would be 5/2 t to the 3/2. And natural log of t would be 1 over t, so it'd be 2 over t. And that's it. That's your derivative vector. And now the next one, here's 18 right here. It's t cubed, cosine of 3t, sine of 3t. So the derivative of t cubed would be 3t squared. And don't forget the chain rule. So the cosine of 3t is not just negative sine of 3t, it's negative 3 sine of 3t. And then same thing goes for the chain rule on this one. You have to take the derivative of 3t in both cases, which gives you a 3. So the derivative of sine of 3t would be cos of 3t. And there's your vector. Okay, just like regular derivatives of functions, you can take second derivatives of this when needed, and we'll be needing that in another section. But okay, it's just like you would think it would be. So this one's asking find r prime of t, r double prime of t, and then r prime of t dotted with r double prime of t. So keep in mind when we do this dot product, that answer is going to be a scalar function of t. It will not be a vector. So let's see what we have. I chose to do this example number 24. And 8 cos t plus 3 sine t. So that one's pretty easy enough to get the first derivative. And it would be negative 8 sine of t. And then the derivative of 3 sine t would be 3 cos t. So the second derivative will be the next derivative after that. So the derivative of negative 8 sine t would be negative 8 cos t. And then the derivative of 3 cos t would be negative 3 sine t. So that would be your second derivative. And then we do a dot product. So these first two multiplied together would be positive 64 sine t cos t. And then 3 cos t times negative 3 sine t would be negative sine t cos t. And then so add those together, we'll get 55 sine t cos t, which is a scalar function. Alrighty, let's talk about this idea of smooth, continuous. So the parameterization of this curve by the vector value function is smooth on the open interval, where when f prime, g prime, and h prime are continuous on the interval, and then r prime of t cannot equal the vector, zero vector anywhere to be considered smooth. So let's take a look at this real quick. This is this number 38 right here, so we'll take the derivative of this and have a look at it. So the square root of t is t to the 1/2, so the derivative will be 1/2 t to the negative 1/2. Then we have 0, t squared minus 1, excuse me, the derivative will be 2t. And then 1/4 t will just have a derivative of 1/4. Now the domain has a lot to do with this here. So the domain, you see these two components would be okay, and we talked about domain in another video, would be t greater than or equal to 0. So it's actually continuous at t greater than or equal to 0, but it's not considered smooth at that point, because you see over here the derivative is undefined at 0. So in other words, it's not continuous at 0. So the derivative is not continuous. So if the derivative is undefined, so therefore it doesn't start becoming smooth until right after the number 0. So it's continuous starting at 0, but then not smooth until after 0. I went ahead and put a graph in with this next one. So here's the r of t. I won't read all that out since you can read that, but let's take a look at the derivative. 5 cos t will be negative 5 sine t. Negative cos 5t will be positive 5 sine of 5t. 5 sine t will be 5 cos t, and then negative 5 sine t will have a derivative of negative 5 cos of 5t. Now, the graph actually gives us away much better than figuring out the actual points. It can be a little tricky to figure this out. But anyway, the point being is that on this closed interval, it's going to be continuous everywhere. There's no discontinuities in here. So it would be continuous everywhere on that interval. But the trick or not is now whether it's considered smooth. And actually, it's not smooth anywhere it's hitting those sharp points. Remember the basic idea in derivatives? One of them is that, if the derivative forms a sharp point, the derivative is not defined at that point. But it's a little tricky. I just sort of figured this out. Well, obviously the picture would have helped me, but this is a little tricky. But anyway, at every pi over 2, I know this would be difficult to figure out without the picture, just kind of more by trial and error, but the picture kind of gives it away. All 4 of those derivative vectors at those points, 0, pi over 2, pi, and 3 pi over 2, form the 0 vector. So anywhere it forms the 0 vector, you're not smooth there. So you see the curve is not smooth at those points right there. And then visually, it's because they're sharp points. Okay. Here's some derivative properties. Now, I don't think you need to worry about committing these to memory too much. I just want to mention a couple of these that, sometimes with properties, and I believe I've mentioned this in other videos too, just because in certain cases with these things, just because there's a property there doesn't mean you have to actually use that property. Now, sometimes in math you have to, like calculus, derivatives, there's times where you have to use the product rule or you have to use the quotient rule. And like, for example, this number 4 tells you that the derivative of a dot product of two vectors is sort of like these are both like product rules, whether it's dot or cross or like product rules. But you don't have to use them because I'll explain why here in a second. But you see it has r of t dot u prime of t plus r prime of t dot u of t, and the same thing with the cross products. Well, the difference between this and just two regular algebraic functions that you could not combine, like if you had like t squared times sine of t, that's why you'd have to use a product rule. So instead of using either one of these two properties, I would not use these properties, especially number 5, because I wouldn't have to take two cross products. Because you can take, in this scenario, number 4 and number 5, you can take the dot product in number 4 and then just find the derivative of that. Same thing with number 5, you can take the cross product of those two and then just find its derivative from there without having to go through this process of doing two cross products. So just because that's a rule in this case, we do not have to use these rules. And here's just kind of some basic stuff here, so they're not too bad. So they're asking us to do for two functions here. They said here's a find r prime, find the derivative of 3r minus u. And then C says find the derivative of 5t times u of t. And here we go, the derivative of the dot product and the derivative of the cross product. So you're going to see that I'm not going to use those rules. I know the instructions are saying use the properties of the derivative to find the following. All right, somebody, if they made you do that or whatever, an instructor, that's fine, but there's no way I would. I'm just looking to get the result by any acceptable method, and those rules in this case are a waste of time. So the r basically is t, 3t, t squared. So r prime would be the derivative of t is 1, 3t is 3, t squared is 2t. So that would literally be the answer for that one. And so for 3r minus u of t, I would not use any properties. I would evaluate what is, 3r minus u. I'd work it out. So 3 times r, just multiply every component here in r by 3, right there. Here's u over here, there's the u vector. So you just take the 3r minus the u, subtract them. So you get 3t minus 4t is negative t. 9t minus t squared is 9t minus t squared. 3t squared minus t cubed. So those don't combine. And then you just take the derivative of that result. So negative t would be negative 1. This will be 9 minus 2t. And the last one, derivative of 3t squared, is 6t, and then t cubed is 3t squared. There you go. Now C says find the derivative of 5t times u of t. So instead of using any kind of rule there, I'm just going to take 5t, multiply it by u of t right there. Then I'll take the derivative. So you can take the 5t and distribute it. So you get 20t squared, 5t cubed, 5t fourth, and then it's easy to take the derivative from there to get this result. Take the derivative of that to get this. Okay, the last one is, the next one, last one on this page, but, well, it's not the last on this page, but anyway. Part D, r dot u. Of course, I did not mention here in D, like I did for E, we do not have to use formula 5. Well, we didn't have to use the formula for that one either, so I guess I could have mentioned that, but no harm. I think you can see what's going on by the result, so it's pretty easy. I'd go back and fix that if I thought it was going to be complicated, but it's not. So do a simple dot product, and you'll get 4t squared plus 3t cubed plus t to the 5th, and then the derivative of that is easy. It'll be 8t plus 9t squared plus 5t fourth. So this is a scalar result here. The first three were vectors, but the fact that we're taking a dot product here means even though it's the derivative of it, we're going to get a scalar. The next one's going to be a vector result because remember the cross product yields a vector. So once again, I'm just going to cross R and U without even taking that formula into consideration right here. I'm not going to worry about that. Here's the cross product formula. So I'm going to trust you'll be able to follow that. I'll just do the first component just to show you. So it's U, well, U and V, R, U, and the formula. The first one's always U, the second one's V. So technically using the cross product, this is U, and that's V. So the second times the third, so it'd be 3t times t cubed would be 3t fourth. Third times second, so it's minus that. T squared times t squared is t fourth. So 3t4 minus t4. So you go through each of those steps to complete that cross product. Now the first one did have like terms, the last two did not, so you might as well take 3t4 minus t4 and just call it 2t4, just for simplicity. And then just take the derivative of that. So 2t4 will be 8t cubed. 4t cubed minus t fourth will be 12t squared minus 4t cubed. And then t cubed, 3t squared minus 12t squared, derivative of that, which is minus 24t. So now it's definitely going to have a vector result. All right, so well, I guess I just decided to use that cross product formula just for fun there. Well, like I said, I'm not going to go through all this, but long story short, it did work. It did yield the same answer. So I'm literally, like what I said right here, I'm using it, doing it that way, where I'm taking the derivative and then doing these cross products. But like I said, I would never do it that way unless you were told you had to do it that way. And then I got the same answer I got right back up here. But I guess I just thought it might be interesting to show that, but I wouldn't worry about that only unless you're kind of interested to see how that worked. And then I guess that was sort of not a mathematical proof, but just sort of informal kind of sort of proof showing you that, you know, my answers matched. So obviously if the answers would not have matched, for sure what I said on the other page would have been wrong. And I just included the cross product formula again. Now, integration of vector valued functions. Well, the integral of a vector valued function is going to be a vector. Now, I'm surprised that the book didn't put that. I just put this in there to show you. So you see, you just integrate each component, and you'll have an I, J, maybe potentially a K, obviously if it's a space vector. And then the C really at the end of this, the plus C is a vector plus C. Like you can't have a vector answer and then like plus some letter C, because remember you can't add, you know, vectors and scalars. You can multiply a scalar times a vector, but you can't add them together. So this has to be C in the sense of a component vector. I guess I could have written it out well. You could think of it like down here as being a C1I, comma C2J, comma C3K, something like that. So the definite integral means you would evaluate them, and then you would not have the plus C there. All right, so let's take a look at these two. Then I believe I have a definite integral coming up. And I don't like for these integrals to get too complicated. You know, in other words, I would never, you know, maybe it may be a basic integration by parts or a basic trig. I don't want to get these out of hand. You're not going to have to do some complicated trig substitution or partial fractions or anything that's, you know, too rough. Now, don't expect it to be necessarily as easy as number 44, but, you know, at least that one's really kind of easy. So I just wrote it this way. There's different ways you can write it. I just did the integrals right up here separately, and then I combined them in the answer. So 4t cubed would be t to the fourth, 6t would be 3t squared, and then minus, oh, I guess I didn't do this one, just I took an extra step for that one. So t to the 1/2, antiderivative would be 2/3 t to the 3/2 with a minus 4 multiple. So that's negative 8/3 t to the 3/2. And then there we have it. T force, 3t squared, negative 8/3 t to the 3/2 plus that c vector. I don't know, maybe like some test banks and stuff might leave that c vector off of their answers or whatever, but don't worry. I mean, in other words, if you're looking at all the answers and none of them have a c vector there, a constant vector, that just means they just chose not to show it. Sort of like when the program Maple software, when it does indefinite integrals, it does not put the plus c at the end of it. I guess it assumes the reader knows. Oh, here's the C1, C2, C3 I was talking about. Oh, and I just rewrote the same answer in standard unit vector form. So they're the same thing, just whether component form or standard unit vector form. Either way. Well, in my world, I don't care. All right, this was a little more interesting. At least it brings in some U substitution and stuff like that. A little more challenging. It doesn't quite get into the complexities of Cal 2 integration, but yet it's at least a little more involved than the last problem. So I kind of like this one. Now, all three of these integrals are going to require substitution. Now, when you're working these out, I just chose to use three different things here, but yeah, I can't imagine any instructor being upset. I wouldn't be, but if you just let them be all U's. But I didn't want them to be all U's, so I didn't want to confuse the reader. So I gave them different substitution letters for each variable. But if you didn't, that certainly wouldn't confuse me as the instructor if a student wrote them all as U's, and wouldn't be a problem for me. But I just thought it was a little easier to do this way. So this one I'm letting U be t cubed plus 2. So du will be 3t squared dt. So 1/3 du equals t squared dt. And then we would have the integral of, which I'll show you here in a second, the result of this. But the integral will be 1/3 u to the negative 1/2 du, because that radical would come up and be negative 1/2. Here I'm letting b be t squared. dv is 2t dt, so you have 1/2 dv equals t dt. So 1/2 e to the v dv is your integral here. Now for this one, you let w be sine of t. dw is cosine of t dt, so then there's no adjustments to make for this one, like there was for the first two. So you just, for this one, it's just straight up integral of w cubed. Let's come down here and see what happens. Okay, power rule for u to the negative 1/2. The basic power rule will get you 2u to the 1/2 here. And the antiderivative of e to the v is just e to the v. And then w/3 would be, using the power rule again, would be 1/4 w/4. Now we have to change them back into their original form. Looks like I didn't bother writing component form. I just went ahead and just stuck only with standard unit vector form here, which is fine. No harm. Now I'll go back up here so we can see what the u's and everything were. So we have 2/3 u to the 1/2, which is 2/3 t cubed plus 2 to the 1/2, I. And then 1/2 e to the v will be 1/2 e to the t squared, right there. And then 1/4 w/4 will be 1/4 sine of t raised to the 4th power. And plus the c vector. Very good. Now this one's a very, very basic integration by parts for the natural log. So whenever you have natural log in there, that has to be your u. So that means your u is natural log of t. So that means dv would just be dt. So du will be 1/t dt, and the antiderivative of dt will be t. So your result here will be uv, which will be these two multiplied together, t ln of t. minus t times 1 over t, right here, dt. And so that just turns out cancels to 1. So it means that now you have the antiderivative of dt again, which is t. So you have t ln of t minus t is your antiderivative. And so that means the first component will be t ln of t minus t. Now the other ones, the antiderivative of 1 over t would be natural log of t. And then the antiderivative of 1 here, and you don't see a 1, but there's a 1 there. The antiderivative of that 1 will be t. So here we have it. So it'll be t ln of t minus t, that's your I component, and then ln of tj, and then plus tk plus the c vector. Now this is interesting. This is one of these things, kind of like an initial condition type of problem. So this one gives you two initial conditions. You might have seen this even back, not with vectors. I'm not talking about vectors, but just you might have seen this back in Cal 1, and if you covered a little bit of Diffie stuff in Cal 2, you might have seen this, but just none of it with vectors. But in other words, it would have been something where you were given, if you said, okay, suppose that f prime of x equals 3x plus 2, and then and you know that f of 1 equals 6 or something like that. That was called an initial value problem. It means you could solve for c by knowing that f of 1 equals 6 business. That means c would actually have a numerical value. And that's what's going to happen here, except this one, we're going to have to integrate twice because we're starting with a second derivative. But we're given two conditions here, that r prime of 0 would equal 2i plus 3k, and then r of 0 would be 4j. So r prime of t that we need will be the antiderivative of r double prime of t. That makes sense. So the antiderivative of negative 4 cos t will be negative 4 sine t. Antiderivative of negative 3 sine t will be 3 cos t. And then plus, I'll call that C1, but I think it's all right if you didn't put the subscript there. I just did it because technically it'll be a different C for the next one, but it's probably okay just to use C. So we've got to find then what this C1 is here. So we're going to put, so we know that t is 0, it's going to have to equal 2i plus 3k. So that's your left side. Now what happens when I put 0 into this right side? Okay, sine of 0 will be 0. Cosine of 0 will be 1, so that gives me 3k. So when I plug 0 into all this, I'll get 3k plus c1. So I need 3k plus c1 to equal this value right here, 2i plus 3k. So if we subtract out the 3k, they just happen to conveniently cancel out the k's. I mean, all we had to do was get this 3k removed. It didn't have to cancel that other side, it just did. But anyway, long story short, that means C1 is going to be 2i. So that means so now we have an I component that we didn't have before. So that means R prime of t, well actually this is R prime of t right here, with that initial condition. So R of t will be the antiderivative of this result right here for R prime of t whenever R prime of 0 equals 2i plus 3k. So the antiderivative of 2i will be 2ti, minus 4 sine t will be plus 4 cos t, and then 3 cos t will be antiderivative of 3 sine of t. And then plus the c2. So once again, I just used two different names for the c's. This is telling me up here that r of 0 should equal 4j. So let's put 0, so we know we got to set this equal to 4j right there. So if I put 0 in here, what do I have? 0 for this one, 0 for that one. Cosine of 0 is 1, so I get 4j. So 4j equals 4j plus c2. So c2 happens to just equal the 0 vector. So there's actually nothing left here and nothing to put in here. But there easily, could have been something there. There could have been like a I, J, K, any combination of components there. But there is not. So there we have it. So the final answer, R of t would equal 2t I plus 4 cos t j plus 3 sine t k. So what's telling you is that vector valued function satisfies 3 conditions. It's telling you its second derivative is going to equal this. R prime of 0 will equal that. And then R of 0 then will equal that 4j. So it's satisfying 3 things. Which obviously you could check that if you wanted to. How about this one? This is a trig one. And the antiderivative of sec tan I plus, trig tan tj plus 2 sine t cos tk, plus it's a definite integral. Yes, I wanted to show you one of those before the video was done here. Okay, tan of t happens to have the antiderivative of natural log of cosine. And that one actually wouldn't be a hard one to work out if you just rewrote it as sine divided by cosine and did u substitution. But there it is right there. So let's see what we had. Looks like I probably just did each one of these individually. So the antiderivative of sec tan then is going to be secant, because the derivative of sec is sec tan. The tan will be negative natural log cosine of that t. And this one, 2 sine t cos t. You can do a pretty easy substitution here if you let u be sine. Du is cosine, so your integral is just 2u du. The antiderivative of 2u du would just be u squared. So that's going to give me a sine squared right there. I guess I forgot that to write that equaled u squared, but I'm sure the reader would have figured that out here, or the viewer. So I've got to put in upper and lower limits. Sec pi over 4 is the square root of 2, and sec of 0 is 1. Pi over 4, you have natural log of the square root of 2 over 2. Cosine of 0 is 1, and natural log of 1 is 0. And then for this one, sine of pi over 4 is the square root of 2 over 2 squared, which happens to be 1/2 because it would be 2 over 4 when you square it. So we have square root of 2 minus 1i minus natural log of square root of 2 over 2j plus 1/2 k, which that's perfectly fine as an answer. Now there's no c at all here because these are definite integrals. I must have seen the answer written in a different form or something or another, but I wouldn't necessarily worry about all this unless you just want to, in case you saw something like that and you needed to rearrange it. But it's just using log properties. There's nothing magical about it. In fact, I showed in the calculator that all 3 of these results numerically are the same thing. So I kind of use log properties and split them up like this. It's got a minus because the minus in front. And 2 to the 1/2 brings the 1/2 down. And 1/2 natural log of 2 minus natural log of 2. Well, 1/2 of something minus something would be negative 1/2 of that something. So negative of negative 1/2 makes it 1/2 ln of 2. Or if you brought the 1/2 back up, it's ln the square root of 2. So I think I did a whole lot of extra work for nothing. I must have seen the answer written in a different way or whatever, and wanted to show the students that how I could make it look like that answer. Okay, let's take a look at another one of those ones where it's an initial value condition, but this one we won't have to integrate twice, thank goodness. Just go from r prime back to r of 0. And we're going to be solving for that c vector. And there'll be a few more terms here. Well, the other one worked out where the c vector ended up being 0, but for the c2 vector. But this one we'll probably get a little bit of everything. But anyway, I'm just sort of showing you here that to group these into a single I, J, K answer when we're done, because you don't really want to have a bunch of loose I, J, K terms. It's better to put them in one set of parentheses and then in front of each I, J, and K. So let me show you how to do that real quick for this one. And the antiderivative of e to the 3t will be 1/3 e to the 3t. So be careful, this is antiderivative, not derivative. The derivative would be 3e to the 3t. But 1/3 e to the 3t, and the antiderivative of sine of 4t will be 1/4 cosine of 4t. Now you could, I usually give these to students in Cal 2 and suggest that, go ahead and, it's good if you go ahead and just know these, because that way you don't have to formally work out U substitution. But yeah, you could absolutely, if you forgot, you could do it by U substitution, but it just saves a lot of time if you know this. But no problem if you don't. And then the antiderivative 4t cubed would be t to the 4th. So now r of 0 is going to equal 3i minus 2j plus k. So I'm going to set the left side equal to that result, 3i minus 2j plus k. I'm going to plug 0 into my r of t vector and solve for c. So you're going to get 0 for this last component, but not for the next two. 1/3 e to the 0 would be 1/3, because e to the 0 is 1, and cosine of 0 is 1, so you have a negative 1/4 j here. So here's the equation that we have to solve. 3i minus 2j plus k equals 1/3 I minus 1/4 j plus c. So we have to obviously move these components next to c over to the left side. No problem. So 3i minus 1/3 I over here. And then we have a negative 2i, and then it'll be plus 1/4 j when that moves over. And there's nothing affecting the k, so it stays as is. So 3 minus 1/3 I would be 8/3 I. Negative 2 plus 1/4 is actually negative 7/4. And then k is just remained k because it wasn't changed. So that's what your c vector equals. So now, instead of leaving an answer like this, which just really looks sloppy and not very good, that's what I was saying about, here comes the part, the last step, of just combining them into one group term for each I, J, and K. So especially if you had even more components of I, J, and K, that would look even worse. So all I'm basically doing is just grouping terms. So here's an I term, here's an I term. Not difficult at all, just kind of cleaning it up. So I have an I here, so parentheses for I will give me the 1/3 e to the 3t. And let's see, so we group the j components together. I have a negative 1/4 cos of 4t and a minus 7/4, so that groups together with the j. And then the k components, there's a t to the 4th, and you see nothing there. There's really a 1 there in front of that k. So it's t to the 4th plus 1 all times k. And that makes your answer look nice and clean with everything in terms of just a single I, J, and K. And that concludes this video on differentiation and integration of vector valued functions.